So here we are, and before we start to discuss about multiple regression model, and then of course we will apply multiple regression model via GMOV as well as in SPSS. We can only briefly recap basic results from simple regression. So last time we analyzed data set about floods in one of Czech regions. In our data matrix, we have 263 floods. But for analytical purposes, we decided to omit one extra big flood. This is the row number or case number 155. And we made this omission by filtering data. So if you would go into data, you can find via filters that we omitted all floods that are above 200 square meters. So that's the first case, and that's why we have two omitted cases. First one is the big flood on the row number 155. You can see here red cross, as well as red cross is applied to the first case in our data matrix, as there is no size included, so that's why it is also omitted. So that's why if I apply descriptive statistics, I can find descriptive statistics for only 261 cases for price and size, and here we have basic descriptive statistics, so it means at least mean, median, standard deviation, minimum, and maximum. If I would briefly recap previous results, we try to compute classical Pearson's correlation coefficient. If you go into analysis, so you would go into regression and find correlation matrix. That's the procedure for classical correlation, which can perform correlation based on Pearson's formula, as well as correlation for ordinal data based on Spearman or Kendall's tau. So here we have our correlation matrix, and the most important result for us is that the correlation between sizes measured in square meters and prices measured in Czech crowns is approximately 0.7, which is quite big relationship between these two. That's positive relationship, and we can also evaluate statistical significance of this result, as the p-value is quite low one. So we can say that it seems that this relationship will not be available only in my data set, in my sample, but will be available in broader population of all floods from this selected region. And we also included computation of confidence interval here. It is computed by so-called Fisher transformation. The possible output, which is also accompanied with correlation matrix in GMOV, and the same style is applied in JESP, is a plot which is measuring relationship between these two items. So it means between size and price. It is automatically fitting also regression line, as you can see. And if you ask for something more, you can see also density charts for size and price. And also here in the last part of this chart, you can see correlation and also stars as symbols for statistical significance. So this is how it works for correlations in GMOV. And once again, the same style is applied in JESP. Maybe that you remember from previous lecture that in SPSS, you need to perform two procedures. So it means that for correlations, you would find correlation and bivariate correlations. And if you would like to prepare a chart for the plot, you would need to find charts in SPSS. So it's not in one dial. And the next result we try to apply was a simple linear regression model for relationship between the price and size of the floods. First result, the table which is called model fit, is offering our R value, and R value for simple regression is nothing more than Pearson's correlation coefficient. So here we have, once again, approximately 0.7. And usually for regression, we mostly prefer to interpret so-called R square. It is called coefficient or index of determination. So it's nothing more than second power from R. So here it is approximately 0.5. And usually for interpretation, we apply multiplication by 100, and we use percentages for final interpretation. So here we can say that nearly 1/2 of the variance of prices, it means prices of flats, can be explained by their sizes. So it is, from substantive point of view, quite nice result, as you can understand. So, of course, it doesn't mean that we are not able to explain more than 1/2. If we would add some more other predictors, maybe we would be more successful. But by only one predictor, we are able to explain nearly 1/2. That's quite good result, at least according to my opinion. Here we have next output, which is not necessary to ask for if you apply only simple regression. It is output which is mainly designed for multiple regression. So it means for regression with more than one predictor, but it is classical so-called Anova test or overall F test for regression, which is saying whether at least one predictor is statistically significant or not. So we will discuss about this output later. And the most important output for us is the last table, model coefficients. You can see that if you click into individual outputs, you can see also input dialogues in Chemovi. The same style is applied in JASP. And you can see that for this classical output with model coefficients, we received two coefficients. First one is called Intercept, and the second one is called size. And it means, once again, Intercept, if we go back into our picture, the meaning is this value. So it means it is the size of the intersection of vertical axis, y-axis, and our fitted regression line. In other words, it is the value of dependent variable if independent variable is 0. So once again, here, and once again, interpretation is totally rubbish here, would be following. If I would try to buy flat with 0 square meters, I will not pay, but those will be paying to me approximately 30,000 Czech crowns. Once again, 0 square meters, there are no such flats, so it's total nonsense. But this would be the meaning of intercept or constant. In a few minutes, we will try to make some changes in data that can help us to interpret also this intercept or constant. So we would learn how we can transform data easily to save the interpretation of the intercept. But the most important results usually is the influence of individual predictors on dependent variable. So here we have only one predictor, so it means that the most important result for us is this value, 14,000 and approximately 300. And we can use two interpretations here. So the first one could be, if I increase the size of the flat by 1 square meter, the average increase of the price would be approximately 40,300 crowns. So that's the one possible interpretation. Second one, and maybe even more simple, would be that according to our model, the average price per square meter is 14,300 square meters. So you can select one of these. Both of these are possible. I would say that the first one is classical for regression, and the second one is maybe from substantive point of view, in this case, better. So that's interpretation of this coefficient. And if you take the coefficient itself divided by its standard error, usually called as SE, or sometimes another shortages can be applied in another packages. So if you take the ratio for these two, you would get T value, which is based on so-called partial t-test, which is approximately 15. And here we have also statistical evaluation by p-value of this t-testing. Null hypothesis is saying that size is not influencing price for the whole population of flats in this region. And alternative is saying, okay, there is some influence, at least some there is. And here we have small p-value. We set up a classical alpha statistical significance, such as 5% or something like this. So we would conclude, okay, it seems that also for all flats in this region, size is influencing price. But according to my expectation for this case, there would be no doubt we would reject this null hypothesis. So maybe that's useless to apply the test for this data. And we added also two outputs here for this table. We ask for confidence interval, which is not automated output. The same style can be found also as PSS. So you must also ask for confidence interval. So we here have a rough estimate of possible impact of size on price. So it could be as low as 12,001.5, and it could be as high as approximately 16,200 Czech crowns. So the average price per 1 square meter could be somehow differentiated in the population. In the sample, the average price is like this figure. So here we have, we can also go into these model coefficients, and here we can see that here we can ask for this confidence interval, and we also ask for standardized estimate. And once again, if you apply standardized estimate for the slope, so it means the relationship between size and price here, so you would get correlation coefficient once again. So that's another option how we can ask for correlation coefficient via simple regression dialog. So it is standardized estimate as well as R in the model fit table. So here it is. And before we would go further to the next step, we would try to change the meaning of the intercept and also the value of the intercept. So it means to find some point for which this value, so it means value above 0 on horizontal axis would have some meaning. There can be many possible solutions for this task, but the simplest solution and the most common solution for this case is called centering. Centering means that I would take original data. So if I go into our data matrix for the predictor, so here we have sizes, and I would first of all try to compute the mean or average for these sizes. So here we have descriptives, and we can see that the mean size is approximately 65 square meters. And if we know that this is the average size, I would prepare new one variable, which will be called centered size. And it would follow this logic. If the size of the flat is above the mean, it would get positive values. And the bigger size above the mean, the bigger will be the centered size variable. But if the size of the flat is below the mean, it would give negative value. And the bigger is the difference between mean size and real size, the lower the number of the centered size will be. So the computation will follow the logic. We would get size values, and we would subtract the mean from all these values. So let's imagine the first flat is 50 square meters. So centered size will be minus 14.7. 50 minus 64.7. For the next flat, 82 minus 64.7, etc., etc. So this will be centered variable, and once again, 0 would mean this is the flat with the average size. So it is somehow substantively interpreted value. So in the next step, via regression, the constant or intercept would mean, okay, what is the average price for flat with the average size? And that's possible to use for interpretation. So that's the first introduction into this procedure that is called centering. And I can assure you that for regression analysis, as well as for some advanced statistical techniques that are based on regression style of modeling, this centering is very often applied. So this is the first introduction into this centering topic. So if we would need to compute this centered variable, we would need to click into compute. And here we would get a new one column. And you can see that new one column is called as C, but I would propose as it would be understandable for us very simply to add some variable name that would help us to understand what is behind. So I would type small c as it is centered, and I would add size as it is based on original variable size. So here we have variable which is called C size, centered size. You can add also description if you like, but that's not necessary. And we would need to apply some formula. So the formula would be that I would take the size. So I would need to go into this window for this computational formulas. So I would type size. Be careful, size with small letters, as once again, CHESP and GEMOVI are case sensitive, as R is case sensitive. And then we need to subtract, so minus, and 64.7. And I guess that point is a decimal separator here. So 64.7 would be, I hope so, correct formula. If you click into enter, I hope it works. So you can see that C size for the first flat, it means second row in our data matrix, is minus 14.7. So it seems correct. For the second one, it is 17.30. It seems correct, etc. So I guess that currently this variable is prepared for us, so I can close this dialog. And I would propose for simplicity, for checking also, to go into these descriptives. So it means into the first table, and to check this new one variable, C size. So I would ask for C size as well. And we would see new one column here. And as far as we slightly rounded the mean for size, we used only the first decimal, so we can see that the mean for C size is not perfect 0, but it is slightly below 0. So it is the only effect of rounding, but I guess we can omit it. But it is correctly applied formula. And if everything is correct, so standard deviation, so it means the variance of size and C size must be the same, as we only transform the scale by the mean. So we only change the mean of the variable, and you can see the standard deviation is 20.1, 20.1 for both variables, so seems correct. And you can only check that minimum and maximum must be shifted down by 64.7 units. So it seems once again that all these transformations were correctly performed. So here we have only a small check of the C-size variable. And currently, I would go once again back into data matrix, and we would only briefly recompute our previous results. So it means we would take, once again, apply linear regression model. It means simple regression, but instead of size, we would apply C-size. And we would get, I hope so, nearly the same results, only the difference would be here in the first row for Intercept. So it means here we would get estimate, which would be different from this value. And can somebody once again repeat me what would be the meaning of the Intercept with C-size variable? What would be the meaning of the Intercept or constant? It would be the average price per flat with the average size, yeah? Okay, so let's go back into analysis. Let's go back into regression. Let's ask for linear regression. And here we have once again dialog. So dependent variable once again is the price. And independent variable is currently not size, but C-size. So it means centered size. And it is cardinal dependent variable. That's why we define this variable as covariate. So here we are. We have first results. Only for comparability with previous results, I would ask for model coefficients here. I would ask for standardized estimate, for confidence interval for estimate, and also for Anova table to have the same result as previously. So let's go very quickly through first two tables. So in the first table, we have the same result as previously. So it means that the percentage of explained variance must be the same if we only center the predictor or more predictors. So the level of the explanation must be still at the same value. So here we are. We can skip Anova table, but once again, if you would compare this Anova table and previous one, it must be all the same. And what is slightly different for the last one table, so it means table with model coefficients, is the first row measuring the intercept. So here we have approximately 900,000 value. And once again, the meaning of this value is currently. This is the average price per flat with the average size, and we know that average size is approximately 65 square meters. So this is, or maybe correctly, it would be to say this was approximately 6 years ago, the average price per flat is the average size in selected region we have in our data. And of course, that currently may be that it could be also possible to go to statistical testing here. So it means the small p-value that it is improbable that the average price per flat with 65 square meters is 0. Once again, it's nearly nonsense to apply this test, but here we can apply this testing. And for the second row, if you would compare with previous table, all figures must be the same, as C-size is the same variable, I mean, in their explanatory power as original size. So all these figures must be the same, including standardized coefficient and confidence interval. So I guess there is no necessity to interpret this second row. Okay, so that's, I would say, very simple trick how we can interpret constant or intercept in a regression. So it means we can somehow transform independent variable or predictor by centering. Only I would like to say that if you would have more predictors than only one, and all of these will have 0, which is not substantively interpreted. So for all these predictors, you would need to prepare this centering. Another option, or another simple option for this transformation would be that we can take minimum value as the base as 0. We can take also maximum value as the 0. We can take also median value as the 0. So similar transformation can be performed by minimum, maximum, or median. But this centering, and sometimes it is also called as global or grand mean centering, as we apply the mean for all data included in our sample, is the most common procedure for this data transformation for possibility to interpret constant or intercept. So here we are. There are some questions. We are currently leaving the topic of simple regression, so now it's a good time to asking questions, and then I would start a slightly advanced topic of multiple regression. So it means we would add more predictors into a model. Okay, so if there are no questions, I would go further. And before we will go into real-life computations, first step would be to follow some slides from PowerPoint presentation. So first of all, here we have the picture, once again copied from Field's textbook, and this is only a graphical presentation of multiple regression. This is the easiest case of multiple regression in which we have only 2 predictors and 1 dependent variable. So it means that, once again, this vertical axis is dependent variable. Once again, here we have the case of record sales in thousands. And here we have on this plane, I would say downstairs, 2 independents, number of plays on radio and advertising budget. So here we have 2 independents. And here we have also the picture explaining the meaning of individual parameters or coefficients that will be applied in multiple regression. So once again, there will be some constant. And you can see that the constant is the intersection of vertical axis. And here we do not fit regression line, but we fit this blue shape, and this blue shape is called plane. So we are applying linear regression plane if we are in 3-dimensional space. So it means if we have 3 variables. And this plane is described by the beginning or constant. So once again, intersection of this plane and vertical axis in the point which is 0, 0 for both predictors. And you can see that the plane, if I rephrase it non-mathematically, has 2 directions, this one and this one. And these 2 directions, and you can find it here by some descriptions, would be 2 regression slopes. So it means the importance of number of plays on radio. So it means first predictor, and the importance of the second predictor. So we will take 2 slopes. So it means influences of the first and the second predictor. So this is the meaning of 3 parameters in multiple linear regression for 3 variables: constant or intercept, the first slope, and the second slope. So this is multiple regression for 3 variables. So it means 1 dependent variable and 2 predictors. If we would go to 4-dimensional space, 5-dimensional space, and more dimensional spaces, I guess maybe it would be complicated for you to imagine, but it's possible. So we would only replace this shape, which is called plane, by something what is mathematically called overplane. In Czech, for three-dimensional spaces, we call it as plocha nebo rovina, and for more dimensional spaces, we call it as nadrovina, nadplocha. So that's only for Czech students. And currently, we would be trying to interpret at least two slopes or more slopes. It depends on number of predictors and also the constant. And we know that we can interpret the constant or intercept only in the case if there is some zero which has substantive meaning, or if we center data as we applied this step for previous computation in simple regression. Before we start to compute, I would go briefly into some computational details. So maybe that at least some of next slides will not be very nice, but please don't ignore these slides as they can help you to understand formulas in some textbooks and books and articles related to linear regression. So I would like to go into the realm of vectors and matrices currently. So if you didn't visit this sphere previously, please try to follow these steps. So let's imagine that I would take some four predictors for simplicity. So I would call usually these predictors as x1, x2, x3, and x4. Every predictor or values for this predictor, so it means this column, would be called as vector. So vector is usually one column in my data matrix. And if I would merge together more vectors, and these could be related somehow, as I would like to apply, for example, four predictors. So if I would have the shape that is based on rows and columns, so it means it is the set of individual vectors, we call it as matrix. So matrix is simply table with rows and columns, and individual columns are usually created by individual variables. So that's the meaning of the shape, which is called matrix. We know also that general command to this shape is also called as data matrix generally. But usually in regression, data matrix is based on independent variables only. For mathematical reasons, and take it as it is, usually we add also artificial first one column to this data matrix of independent variables. And this artificial column, and once again, we do not need to enter this artificial column into our data as PSS or Gemovi or Chess will do it for us. But this first column is so-called unit column. So it means only codes as one will be included in these. And the mathematical reason behind this artificial column for data matrix of independence is that these units or one codes are in data matrix, as we need also to estimate constant or intercept. So intercept is based on the logic that it is slope or coefficient in regression based on predictor which is only codes one or unit numbers as the base. So for mathematical reasons, the first one column in data matrix of independent variables in regression, we add unit column, which is the base for computation of the intercept. So that's some artificial step which is behind the scene. Okay, so this is data matrix and how it works. And you can see from this data matrix, for simplicity, the data matrix for regression can be based on figures. So it means some cardinal variables, but it can be also based on binary variables. For mostly computational reasons, at least in classical statistical packages such as SPSS, CHASP, and GEMOVI, it is good to recode previously these yes, no's, or may females into 0-1 coding. So that's only, once again, technical step which could be performed. So here we have set of independence, and once again, artificial column with unit as the first one. On the, I would say, right-hand side of the equation is the set which is called vector y. So it means values for dependent variable. So in our case, if I would go back into our data, so let's imagine that this column of prices is the vector of y. So it means a vector of dependent variables. So this column is creating one column with dependence. And then we would have size or C size. And before size and C size, we would get one artificial column with unit values. So it would be our matrix of independence and vector of dependence. So that's the base for computation of regression. And of course, you can imagine that you can have more columns in data matrix for independence. This number is not, at least theoretically, limited. And if I would go to the next step, my main goal is that I would like to estimate vector of so-called betas. So beta is the general symbol for estimated value of the coefficient, and coefficient means intercept or constant, and also individual slopes. So once again, if I go back into the picture from field, so this is beta 0, beta 1, and beta 2. It would be classical discussion about these individual coefficients. These betas we are discussing here are population values. So it means usually we don't know these values and we will not know these values. Only the exception would be if I would get all population data, then I would be able to compute these betas. So instead of betas, in real computation, I would get estimates from my sample. And that's why usually constant is not discussed as beta 0, but it is discussed as B0, small b. So instead of this big letter from Greek alphabet, we use small b from Latin alphabet. Instead of the impact of the first variable, so it means first slope for population, beta 1, we would use B1 as the estimate from my data, etc., etc. So this is only the difference between betas and small b's. So beta is the population parameter. We are not able to acquire this, and their estimates are usually discussed as small b's. So, and if we have, for simplicity, as we have here, 3 independent variables, so we would be trying to estimate intercept, impact of the first variable, impact of the second variable, and impact of the third variable. Sorry for this mistypo, beta should be here. So this would be regression coefficients or slopes for individual predictors. And also, from mathematical point of view, this beta, which is in bold here, is the vector. So it means this is the column created by all these values. So this is also, from mathematical point of view, column based on these individual values of these estimates, intercept, and regression coefficients. So that's it. And here we are. And let's start with, I would say, simple equations, as the next slide will be maybe even more simple, but a little bit complicated, as instead of individual coefficients, as are here, we would be applying these vectors and the matrices from previous slides. So here we are. So the general regression model or linear regression model for the population is based on following formula. I would like to explain some dependent variable called small y by some average value, so it means the value of the intercept or constant, the impact of the first variable, so it means multiplication of the first slope and the level of the first variable. The same for the second variable, etc. And last one variable for simplicity is called as P. So P is usually number of predictors in a regression. That's the general symbol. And as far as we are able usually to explain some variance of dependent variable, there is also usually some unexplained variance. So it means that usually linear regression model or another regression model from nonlinear realm is not explaining everything. And that's why we have here also this epsilon symbol, which means there is always something what we call in statistics random error, or in other words, unexplained variance. So we do not expect to explain fully our dependent variable, and that's why we are applying this random error. So this is general model for population. If we subtract from this equation this epsilon, which is once again unexplained variance or random error, so we would try to estimate, and that's why here we have a big E and Y in brackets, something like average level of dependent variable. It is only estimate, and this big E is instead of English expression expected value. So it means some mean expected value for the population is in other words mean. So if I try to estimate the mean of dependent variable, I am using this regression formula without any random errors. So these are omitted. And unfortunately, I usually do not have data for the whole population. So I do not know values of Y and X for all units in the population, but I have only data for my sample. And that's why I am using some formulas for estimation. These estimations are based on the sample, and that's why, and we know about this difference from previous discussion, instead of betas, I am applying B or small b's. So B0 is the estimate of the constant or intercept based on my sample. B1 is the estimate of the slope based on my sample, etc., etc. And once again, last one variable is usually applied with the index small p. So here we have what is our real data saying. So it means we have only estimates. So once again, be careful. If you are applying linear regression model, and also the same logic can be applied to nonlinear regression model, every time you have usually only small b's, so it means estimates from the sample. And as far as we have only estimates from my sample, we are trying somehow to infer results to the big population. And we know that we try to apply statistical tests, such as especially partial t-test and confidence interval for this generalization. So that's why we apply these tricks. And now we will try, I hope so, to make these equations easier, but maybe slightly more complicated. So if I try to rephrase this model, so it means this model for population by vectors and matrices we discussed previously, I can type only this equation, that I can take dependent variable vector. If it is in bold in mathematics, so it is every time vector. So once again, it's column of all dependent variable values. Big X, once again in bold, is once again matrix for all independents and once again, this additional first one column with units. And it is multiplied by beta coefficient, and we have here also the vector of random error. So for every individual, there must be some disturbance or random error. So it means some difference between regression, estimate, and dependent variable. If you are familiar with computation with matrices and vectors, so maybe that somebody could find the mistake which is present here in this formula. Is somebody capable to find the mistake here? Do you know something about multiplication of matrices and vectors? I guess that at least our students float some mathematics with computation with vectors and matrices. So if you do not remember, I can inform you that this beta couldn't be before x, but should be here. So correct formula must be here, as computation of this multiplication would go like these values multiplied by betas. If it would be reversed, it couldn't be multiplied at all. So results would be nothing. So this is only correction of this formula. So that's only some short introduction into matrix algebra or vector algebra. How is it called? And if you try to take y, so it means vector for dependence, minus this regression estimate, and you try to find the logic of ordinary least squares. So it means you will try to find the smallest value of the second power of this difference. Please believe me, we wouldn't go into mathematical proof. So you can find the formula for the estimate of individual coefficients. And it can be computed like this formula is saying, so maybe I can make it bigger slightly. So here we are. Let's try slightly to explain what is behind this computational formula. So it is saying that the first time you would take your matrix for independence, and you must only, this is this transposition sign, to take this matrix and reverse rows and columns. So instead of rows, you will get columns. The opposite is true. And if you take this matrix and multiply it by the same matrix, not transposed, it is the first result. Then the next step is, here it is, -1. It is called inversion for matrices. This is a mathematically defined procedure. Inversion from mathematical point of view means that if you take original matrix and inverted matrix and multiply both of these, final results would be the matrix with units only. So that's a formal definition for inversion. So you will take this data matrix, multiplied, inverted, then once again multiplied by transpose matrix of independence, and the last step would be multiplied by vector of dependence. If you do not understand fully to this magic, that's maybe not necessary. I hope that at least some insight were performed previously. Here you have also some links to quite good web pages about computations that are behind the scene. But this is how it works in statistical package. So it means that statistical package would follow this formula and would compute for you estimates of constant or intercept and individual slopes by this formula. So it is, I would say, only simple vector algebra behind the scene. And if I would spend, I guess, 2 lectures on computations, it means by pencil and paper method, I can assure you that you would be able to compute real-life regression also by hand. Of course, I will not force you to do it if you have computers, but it's not so complicated stuff still. For further lectures, so it means for some advanced models, there wouldn't be such easy chance to compute it by hand. So that's why we would apply computers from the beginning. And also, I would like also to save your time, as I expected, for example, prices and sizes, we were computing in something like seconds. Your hand computation would take at least minutes, maybe 20 minutes or something like this. So that's why we would be using computers. So that's all about estimation and how it works. So here I would only rephrase not chess, but currently we are using GEMOVI, and multiple regression in GEMOVI will be very easy. So we would get result which would be equation of line, plane or overplane if we have 1, 2 or more predictors, and we would get also statistical tests, we would get coefficients, we would get details about regression diagnostics. Maybe we would start something today, maybe that next year, next week. But now I would start to compute some multiple regression case here in our data set through GEMOVI. And we will also try to perform similar procedure in SPSS, as you will recognize that these are very close to each other. So once again, here we are in our data about flats. And if we would like to apply multiple regression, of course, it's necessary to apply the same procedure. So once again, let's go into regression. And let's select linear regression model. So here we are, and we need to take, once again, price is dependent, as this is the variable we would like to explain. I would once again take C size as the first covariate. And for simplicity, I would ask maybe for the next one variable, which will be whether the flat is reconstructed or not. So it means whether some building procedures were performed in, I guess, last 10 years. So before we enter this variable into a model, I would be happy if you can help me and give me the estimate whether reconstruction will have positive or negative effect on the price of the flat. So is your expectation that the price will be increased or decreased by reconstruction? Increased, okay. Only to have some idea about. We need only to move reconstruction into factors, as it is a nominal variable coded as 0, 1. 0 means no reconstruction at all, and 1 means reconstruction. Once again, predictors in linear regression could be 0, 1 coded, binary, or cardinal variables. So here we are. You can see at least some basic results. Before we start to interpret our results, I would once again propose to go into model coefficients. Here we are, and ask for Anova test, for estimate of confidence intervals, and also for standardized estimates, as currently we are discussing about 2 predictors. And maybe the question could be also which of these 2 predictors, so it means whether it is reconstructed or not, and size of the flat is the more important. So we have one more question from previous discussion. So before we start to go into I would say the most important tables, I would go briefly back, and let's only recap that original R was 0.685 and original R square was 0.47. And if I would add one more variable, I can see that the increase of R or R square, and mostly we are discussing about this R square, is very small one. So it means that reconstruction is maybe not too important, or there can be also another reason for this small increase. If bigger flats, for example, would be all reconstructed and small flats would be all not reconstructed, so maybe these two variables would be perfectly correlated, it could be also the cause why we have this small increase. We will discover what is true pattern in our data. But let's go into this Omnibus Anova test. And here we have some answer for the question that reconstruction, at least from this p-value, is not very important, at least from formal point of view by statistical testing. So that's the first insight. But here we have a detailed table, and let's go through these results. First of all, we have here Intercept, which is 875,000 Czech crowns. And before we would go into details, I would be happy if somebody could help me to interpret this value. So what is this estimate saying about prices of flats? For which types of flat this is the average price?
For average size flat.
For average size flat, and for reconstruction, it is reconstructed or not. We are discussing about zeros for independence. So this is average size flat. Sorry?
Not reconstructed plot?
Not reconstructed, yeah. So once again, if we have more predictors in our regression model, and of course they are centered or zeros are possible to interpret substantively, so the intercept or constant would be the average level of dependent variable if all independents are at zero level. So here it is the average size flat, once again, approximately 65 square meters, and not reconstructed as it is zero for reconstruction. So this is the meaning of the intercept. So that's the first step. Second step, C size is once again still nearly the same estimate, so approximately 13,300. So once again, this is the increase of the price by 1 square meter. Once again, very small p-value, quite narrow confidence interval, and standardized estimate, once again, saying quite big impact, 0.684. And let's go to reconstruction. So first of all, from substantive point of view, 53,000 approximately, we will pay more for reconstructed flat. So that's not very big amount of money if you compare this value to the intercept. So that's very small increase from substantive point of view. And once again, this value is valid only for my sample. And now the question is still possible that reconstruction means some increase in the price also for bigger population of flats in selected region? And we have two answers for this question. First of all, p-value for formal partial t-test, saying 0.171. So for classical alphas, such as 0.05, or slightly bigger, 0.1, or slightly lower, 0.01, are not followed by this p-value. So from classical statistical testing perspective, I would conclude, okay, maybe there is no impact on the increase of the price of reconstruction here based on these computations. And also from confidence interval perspective, which is saying from minus 23,000 up to approximately 130,000, we have doubts whether the reconstruction means increase in the price. So maybe that reconstruction is not of big impact, and maybe there is no impact at all. It could be also the result. Maybe, it will be good also to check that the reason behind the scene why we are discussing about this nearly zero result is that the number of reconstructed flats in our data set is quite small one. So let's check it for simplicity. So I would go back to descriptives. I would move also, oh, it's impossible here in descriptives. So we can maybe prepare frequency table, I guess, at least. Let's see how it works in movie. Let's take recall. Oh, it's possible to compute descriptive, so it's surprising. So here we can see that the proportion of a reconstructed flat is not so small one. 0.4 means that 40% of these flats are reconstructed. We can also check it by frequency table. So here we have 38.7 from this or this figure are reconstructed. So still, this is not a problem in my data. We have quite a lot of reconstructed flat in my data, but still the impact seems nearly zero. And last one column we would like to discuss also, which is called standardized estimate. Once again, it's impossible directly to compare C size and reconstruction, as if we would perform such comparison, we would say, okay, it seems that reconstruction is approximately 3 times more important than size. But incomparability of these two coefficients is very easily discussed. C size is measured as something like the scale from -40 up to +40 or something like this, or maybe even more. So it is quite a long scale, and reconstruction is only 0, 1. So these scales are not comparable, and that's why these two coefficients are not comparable. So I'm not able to say which variable is more important based on these. We usually call it as rough estimates or unstandardized estimates. But if you go into standardized estimates, so these two variables, so it means C size and reconstruction, are transformed into standardized variable. So it means variable with 0 as mean and 1 as standard deviation. So these two results are comparable across variables. And here we can see that C size impact is approximately 5 times higher. So the importance of C size is quite big one, and importance of reconstruction is quite low one. So if I conclude very simply, and we would of course follow this example after the break. So here we would need maybe to take some more and other variables than reconstruction into our model, as reconstruction seems as nearly useless variable for explaining of prices. Fortunately, we have at least some more variables. We can, for example, add whether the flat is new or not. We can also add, for example, information whether the flat has a balcony or not. And we can also add, and we will discuss about this city size as the predictor of the price. So we have at least some other options. So we have at least some more options to apply better multiple regression model. Here, if I would decide whether to apply this current model or previous one with size only, I would prefer maybe previous model, as this model will not help us at all. So it would be my first, I would say, preliminary conclusion for this first insight. And as we are currently reaching approximately time for the first lecture, so I would stop sharing and recording, and we would follow next steps in 10 minutes, so 9:40. So